Moving on to chapter 2, first order differential equations. 2.1, there's actually not even homework assigned in the book. But it's just an introduction, and it looks at a few different things, but mostly free-falling bodies or objects. So check that out on your own, just to kind of familiarize yourself that this is, the beginnings of this stuff should be familiar to you. So then we're going to go on to 2.2, which is on separable equations, and we kind of at this point begin our study of all these different types of differential equations to start solving. So this is what they refer to as a simple class of first order differential equations, and it has this basic form. So the form of a separable differential equation looks like this. Basically isolated on one side. dy dx is equal to a function of xy, but the key is that f of xy can be rewritten. So f of xy, the form is dy dx, and so it must be that there's an and statement there. So and can be, and I'll say algebraically, rewritten to this form to h of y dy, so all one variable like that, and then g of x dx. So that's the form we want to have. So the original form can be this. The original form might look like f of xy equal to g of x times 1 over h of y. And, you're flipping it all around and all that. So it just depends on the form. But the key is you can separate out f of xy into two separate functions. So those are just the different ways to rewrite f of xy. But this really is the key. You need to be able to rewrite it. So all of your y's and all of your x's are all on one side. So for example, let's take a look at a couple of types. So if I have dy dx equal to y squared e to the 3x plus 4y. And then let's do another one. So dy dx equal to y plus sine x. So which one is separable and which one is not separable? So this one, as it sits, looks like you can't separate that. Well, I mean, you need to do some algebra, basically, is what I'm trying to say, to simplify that one. So this one actually can be separated, and this one, because of the addition, you cannot. So the first one is separable, and then the other one is not. Well, this one is not. It's kind of a sentence, right? All right, so let's look at just the general method to solve those. So we'll call this the general method to solve separable differential equations. So it's given by this. So if you have dy dx equal to f of xy, then that you would need to be able to manipulate it like this. So that is a function dy dx, and then you basically separate this out algebraically into two separate functions, g of x, h of y, and then you basically multiply on both sides or divide on both sides to get dy on one side and dx on the other. So rewrite it as p of y. We just don't want to have like look at it as fractions, so, or denominators. So look like that and this. So P of y is P of y dy equal to g of x dx is the form you want. And then you integrate both sides. So you integrate P of y dy, and then it's integrate g of x dx. So you have to be able to integrate on each side, single variable with respect to that, whatever variable's there. Okay, and then you evaluate, if and only if. So you get capital H of y equal to capital G. So those are the antiderivatives, right? And then plus C. No need to write two different constants. We're going to put that down because they just add up, right? You can just subtract on both sides and get rid of a constant. So no need to write two constants. Okay, let's look at an example. And most of the time I'm going to pick the first example that is not in your book because I want you to have as many as you can find. So this, I have other books I'm using to that are very, almost exactly like that. That's in the book are very, very similar. Oops, I forgot to say solve. And then usually I pick one right from the book as a separate example, or if I feel it's enough, we'll do that in our problem sessions or problem sets on Zoom. Just kind of depends on the nature of the content, really. So this one, but I almost always will do an example. So solve 1 plus x dy minus y dx equal to 0. So that's how it's given in this case, which actually in this situation was slightly different than the first few examples I saw in the book. But you can see you want to be able to separate that. So you need to get this factor together with the dx and then the y together with the dy. So you have to manipulate this and get it all on the correct side. So what we can do first is basically we'll bring this over and then divide by the y, but I'm going to flip it. So a little bit of manipulation, you can see you get dy over y equal to dx over 1 plus x. Okay, so now integrate both sides. And you have the integral of 1 over x dy equal to antiderivative 1 over x dx. Okay, so both of those are what form? Okay, so we should remember that. Those are both natural logs. So ln absolute value of y plus, equals, not plus, equals ln absolute value of 1 plus x, and then plus some arbitrary constant c. So that's where you only need to do it on one side, because if you put a plus like c1 and a c2, then you just can subtract c1 and you just say c is equal to c2 minus c1. It doesn't matter, it's just some constant. It's all arbitrary anyway. All right, so then from here, we can still solve for y, right? So if you evaluate this and solve, you basically raise each side to e, and you end up getting that y is equal to e to the ln 1 plus x plus c, which is equal to e to the ln 1 plus x e to the c, right, because you're using power property, adding that up. And so it's basically like that, e and e. This becomes y. Right-hand side, I'm simplifying. Okay, continue. And then since e to the c is equal to some just constant in the reals, and it's actually positive reals, but we don't really have to worry about that. We can write it as y equal to k times 1 plus x. So I'm just rewriting this form and making it into k, because that's a more general way of saying it. So that's our solution. So then we have that as a solution. So that's the basic technique. Yeah, we're good there. All right, so just move on to the next question. This is next example, number 23, page 46. And Nagel. So solve the initial, this is an initial value problem. So solve the initial value problem. All right, so it's what's given is dy dt equal to 2t cosine squared y. Given condition, initial condition is y of 0 is pi fourths. All right, so this is the stage where I'd probably have you try it, or I'll do one more, depending on how we're doing here. So maybe pause this and try and work it out. Okay, so now I'm going to continue. So dy cosine squared y. So I'm just doing I'm separating now. Equal to 2t dt. All right, so now I'm going to rewrite cosine squared, 1 over cosine squared as secant squared. So it's secant squared y dy equal to 2t dt. All right, so now I integrate both sides. So then it's secant squared y dy is equal to 2t dt. All right, so then you need to know what is secant squared y. Antiderivative secant squared y is tangent. So that's tan y equal to t squared plus c. All right, so now find c, the arbitrary constant, using the given initial value. The given initial value, or condition, whatever you want to say. All right, so we have t equals 0 and y is equal to pi fourths. So that's what's given. And so what do? All right, so we substitute in. So we're going to take pi fourths, put it here, t put it here, or 0 put it here, and solve for c. So we say tangent of pi fourths plus 0 squared is equal to, oops, I messed that up. That's an equal sign. Is equal to 0 squared plus c. So what's tangent of pi fourths? Pi fourths is 45 degrees, so that's root 2 over 2 for both sine and cosine, right? So that's just 1. So that's if and only if 1 is equal to c. And that's it. Nothing else to solve there, right? You're good. Therefore, tan y is equal to t squared plus 1. Or, if you'd like, you can actually isolate y altogether and say y is arctan, or tan inverse of t squared plus 1. So, messed up my little line there. That's your solution, and so that's the basic technique. This is kind of the simplest case so far as we develop these, and you'll see these as you go do more examples through the book. Okay, so the next step then would be to do more examples that I will probably do in on Zoom or problems together. But you have plenty of knowledge here to try more. That's the basic technique. Not a whole lot of complication. Next is 2.3, which is on solving linear differential equations, and there's a technique to do that we'll go over.